inequations and inequalities. And yes, there is a difference. Okay. An inequation. An inequation is a problem where you're trying to find possible values. Okay. So you'll end up with a pronumeral being the subject. Might be x is greater than, x is less than, or something like that. So it'll have a solution of specific x values for which it's true. There's a very simple one, 5x plus 3 is less than 2. An inequation because we can solve it and come up with specific values for which the statement is true, and the statement is true for x is less than negative 1/5 in this case. Some special types of ones that we look at. Quadratic inequations. So how do we solve a quadratic inequation? Well, it's pretty much the same as an equation, but we have to take into account a few things. So here we go. Multiplies together to give -6, adds together to give 5. So our solutions are x plus 6, x minus 1. Now, if it was an equation, at this point I would say, oh, well, either x plus 6 is equal to 0 or x minus 1 is equal to 0. The logical mistake to make is at this point to go, oh, well, either x plus 6 is less than 0 or x minus 1 is less than 0. Not true. Okay? Not true. So what I do is I think about it visually. Negative 6 and 1, okay, they're going to be part of the solution. In this case, they're just boundary. They're not included, so I'll just circle those solutions. Now, different ways of doing this. You could just test a point to see whether it works. And as you see which part, you think of the x-axis there as a number line. Where am I? Or you can think of the parabola. The parabola x squared plus 5x minus 6. I'm not really concerned where the vertex is. All I'm really concerned about is the x-intercepts and the concavity, and that's enough to solve the problem, because what I'm now really saying is, okay, for what values of x is this parabola below the x-axis? Yeah? It'll give me y values that are negative. And I can look at the graph and go, oh, okay, so it must be when I'm in between 1 and negative 6. And there's my solution. So x is in between -6 and 1. So you can think of it graphically in 2 dimensions with a parabola, or 1 dimension if you just think of the number line. You could just test some points. So another one. Personally, I hate factorising negative quadratics. So the first thing I'm going to do here is multiply everything by -1. But of course, if I change the sign, I change the sign. So it's now a greater than equal one. That one also factorises. So same deal. This time the boundary is included. So it'll be a coloured in dot. And this time I'm saying, when is the parabola above the x-axis? Because it's positive. And it's above on the outside. And what you'll find with quadratic inequalities is you're either going to end up between 2 points or on the outside of 2 points. So x is less than or equal to -4, or x is greater than or equal to 1. So that's the first type of inequation. There's probably a 2-unit level type of inequation. Now we move to a 3-unit level. You won't see these sorts of ones in a 2-unit paper, where pronumerals appear in the denominator. Here's a very, very simple one, of course. 1 over x is greater than or equal to 3. Now, the way I tend to do it is look for the key critical points. So the first critical point is the bottom of the fraction again. It's this problem with the domain. Bottom of the fraction can't equal 0. So I know with my one, x can't equal 0. So that's an exclusion from my solution. There's no way x can equal 0 in this. Then I just solve it like it's an equation rather than an inequation, because it's a very simple thing to solve. 1 over x equals 3. Oh, x is 1/3. That gives me my 2 critical points. And so just like the last one, I can think of it visually now. If I was to put those on the number line, there's 1/3, there's 0. The boundary point 1/3 is included because it's an equal to. X, of course, is not included because we can't have the bottom of the fraction being 0. And the question once again is, well, where am I on this number line? And it's going to be just much like a quadratic inequality. Am I in between these 2 points or am I on the outside? So I can test to see. And if I test x equals -1, I go, 1 over -1, is that greater than or equal to 3? No, it's not. Not included. Logic then tells me I must be in between the two, but just to check, x equals 1/4, which would be in between 0 and 1/3. 1 over 1/4, which is of course 4. 4 is greater than or equal to 3? Yes it is. So that confirms, all right, I'm in between. Again, if you still don't believe me, let's have a look over on the right-hand side. I'll test x equals 1, sub 1 in. 1 is greater than or equal to 3? No, it's not. So there's my solution. 0 is less than x is less than or equal to 1/3. The reason I can solve that like a quadratic inequality is one of the common methods for solving this, which I don't use myself, is to multiply both sides of the equation by x squared. And then it creates a quadratic inequality to solve. And for those who are unsure, the reason you multiply by x squared and not just x, which you would do for an equation, is because you don't know whether x is positive or negative. And so because you don't know whether you're multiplying by a positive or negative number, you don't know what to do with the sign. Do I keep it the same or do I change it? But if you multiply by the denominator squared, you know that's going to be positive, so therefore the sign stays the same. And so that's why in that technique, you just multiply by the denominator squared. It's probably one of the most common methods, but not the easiest. This is the easiest method. Don't know why everyone does it the other way. Let's have a look at one that's more involved. 2 over x plus 3 is less than 5. So first thing I look at, bottom of the fraction, can't equal 0. So I know one of my boundary points is going to be -3. Then I just solve it like an equation. 2 over x plus 3 equals 5. And I get 5x equals -13. There we go. X equals -13 on 5. Because I don't know about you, I think a linear equation is easier to solve than a quadratic equation, which is what you get if you multiply by the denominator squared. So there's my boundary points. Where am I? Am I in between or on the outside? I can just test a point, and it turns out I'm on the outside bits for this one when we test a point. And so there's my solution. X is less than -3, or x is greater than -13 on 5. Now, those of you who have been tutored or private schooled on this method and have probably been shown to do it via the quadratic denominator way, because that's how everyone seems to do it, I would encourage you to try it this way in the exercise so you can make up your own mind whether you think, hey, which is the easier way of doing it. All right, I said there was a difference between an inequation and an inequality. Okay, so what we just looked at were inequations. What is the difference? Well, an inequality is different. It's a problem that... Is there a reason it's on? Okay. It's a problem that you're proving to be true for a known set of values. So the difference is, in the first one, with the inequation, you're trying to find when it's true, for what values it's true. With an inequality, you're saying, I know the values, I want to prove it's true for these values. So it's a very subtle difference there. You will end up with what we're trying to prove, and we solve it the same way as we do identity proofs. You might have tried some of those, trig identity proofs, things like that. Did you do that last year? Trig identity proofs? We'll look at more of those later this year anyway. So, how do we do it? Remember, it's not an equation. It's not an inequation. So you can't start by moving terms from side to side. Because if you do that, you're assuming your statement is correct. But you're trying to prove it's correct. So you can't move things. It doesn't have sides. It's like, I'm starting with the left-hand side. I want to transform it into the right-hand side. I'm trying to change it and show, hey, look, it's the same thing. So after stating what it is you're trying to prove, right, the question might even do that for you. You'll have an algebraic expression, not an equation or an inequation. And you're going to manipulate it into the other expression. And the common ways of doing it. If you want to prove the left-hand side is less than the right-hand side, one way you might do it is you just start with the left-hand side and you manipulate it and you come up with something and go, hey, look, this is less than the right-hand side. And so you've proven what it is. That's one way of doing it. Another technique, because sometimes it's easier to always show things are always positive or always negative. So you go left-hand side minus right-hand side. Now, I know I said you can't move terms. That's once you've decided what it is you're trying to prove. If I said to you, I want to prove, I don't know, let's look at something silly. X plus 2 is always less than x plus 3. Well, of course it is, but anyway. Say I wanted to prove that. I could say, well, look, instead of proving that, I want to prove x plus 2 minus all of x plus 3 is always negative. And it will achieve the same thing. But once I've decided what it is I'm trying to prove, then I can't go moving terms like an equation. So you might decide, oh, well, rather than prove left-hand side is less than right-hand side, I'll move the right-hand side across and try and prove that the left-hand side minus the right-hand side is always negative, or always less than 0. Then, of course, there's another way of doing it where you can work on both sides totally independently. And what you're saying is, over here on the left-hand side, I've got an algebraic expression, and I'm going to play around with that. And then over on the right-hand side, I've got this other algebraic expression, and I'm going to play around with that. And I come up with two things, but I notice the answer that I got over on the right-hand side is always bigger than the answer that I got over on the left-hand side. So therefore, the right-hand side is greater than, or the left-hand side is less than the right-hand side. So there are different ways we could do it. So my new left-hand side is less than my new right-hand side. I've manipulated them totally independently of each other. So therefore, the left-hand side is less than the right-hand side. Well, let's have a look at proving some of these things. So one of the common ways is starting with a known result, something you know to be true. Because if I start with something that's true, then my argument has to be foolproof, because everyone agrees what I've started with, yes, that is true, and all I'm doing is manipulating that result. So it's a very simple one. We know x minus y is always greater than y plus z, so we know that to be true. We want to prove y is less than x minus z on 2. Okay. So x minus y is always greater than y plus z. I'm starting with something that is true. This I'm allowed to manipulate because I don't have to prove it. It's already true. So I can move terms. Right? So you can only move terms on known things, things that are known to be true, known facts. This is a known fact. It was given to me. So I can move things here. I can say minus 2y then must be always greater than z minus x. And there you go. It falls out quite nicely. I'll divide by negative 2 and I get y is less than x minus z on 2. So I started with something I know to be true and just manipulated that result and proved, oh, well, if that's true, then this has got to be true. Move everything to the left. That's what I was talking about with left-hand side minus right-hand side. So, okay, we're told A is always positive, B is always positive. We want to prove AB outside of A squared plus B squared is always greater than or equal to 2A squared B squared. Okay, looks a bit tricky. I'll tell you what, instead of proving that, I'm going to just move everything to the left. And I'm just starting with this algebraic statement, and I'm going to prove this is always positive. Because if I can show this is always greater than or equal to 0, that then becomes a known fact. I can move the term over and get what we want. So all right, here's this. It's just an algebraic expression. I'm going to show it's always positive. So let's factorise. It's got a common factor of a, b. They've told me a and b are positive. So I know a is positive, b is positive. So now essentially it's this parentheses I want to show is always positive. But hey, look what we've ended up with. It's a perfect square. So that is AB, A minus B, all squared. They told me A was positive. They told me B is positive. We know squares are always positive, or 0. So that is always greater than or equal to 0. That's now a known fact. Well, because it's a known fact, I can now go and move this term across and say, oh, well, therefore, AB outside of A squared plus B squared is always greater than or equal to 2A squared B squared. So that's the idea I was talking about, left-hand side minus right-hand side. Just work with that expression. Here's a fun one. Using that idea, that squares are always positive or zero. It's a classic inequality that we're sometimes asked to prove. So we're told a, b and c are positive. We're going to prove that a squared plus b squared plus c squared is always greater than or equal to ab plus bc plus ac. Okay, I'm going to start with a known result. The known result is that I know squares to be positive. So I know a minus b all squared is always greater than or equal to 0. Now, no one can doubt me on that. If I expand that out and then move to the other side, because it's a known result, I can move terms, then it's true to say then that, well, if a, b, c are positive, then it must be true that a squared plus b squared is always greater than or equal to 2ab. But a and b were just random pronumerals that I chose. I could have just as easily said a and c, and so a squared plus c squared greater than or equal to 2ac. I could have just easily have chosen b and c. So b squared plus c squared must be greater than or equal to 2bc. If I now think of them as three simultaneous inequalities and add them together, I get 2a squared plus 2b squared plus 2c squared is greater than or equal to 2ab plus 2bc plus 2ac. Divide everything by 2, and I've got my result. Okay. So this last bit, the proving inequalities, is probably now more at the extension 2 level. So extension 1, they pretty much cope with the quadratic inequalities. Extension 2, pronumerals in the denominator, and maybe some simple inequality proofs. Extension 2, when we get to that, we'll look at more detail when we do end up doing extension 2, some really good inequality proofs. So, okay, let's have some fun. Exercise 3A.